sometimes, technically, we would say that there's one unique solution here. So sometimes there's some funny language in the book, and that has to do with something, I'll talk about it later in our lesson, but it has to do with something for the fundamental theorem of algebra, which is how we count the number of times a graph crosses. So for example, when a graph goes like this, we call that a root that happens one time, or it has multiplicity 1. But when the root does this and it, oops, computer, we're okay. So when the graph just touches like that, we say that that one, maybe it crosses more than once, twice, 3, 4 times. But it'll be an even number here. This one would cross maybe 2 times or maybe 4 times. And the reason is, when it's factored, maybe it looks like this. So the number 2 is used twice when you calculate it. If you were to expand the whole thing out, there'd be x minus 2, x minus 2, x minus 1. So it gets counted twice. So that's why they say one unique solution, because technically there are 2 solutions, they just happen to be the same number. Okay, so don't let the textbook confuse you there. I'm sure I just confused you enough. So the last one here is 25 minus, let's see, 12 times 9 is going to be 90 and 18, so 108. So that's going to be a negative, negative 783.
It's negative now.
Oh, sorry, the 9's negative. Going too fast. I thought, I was expecting to come up with a negative number here. We'll just say cancel that. Uh-oh. Technical difficulties here. Now, where were we? We were on this one. Okay, so there was a negative 9, so it means it's 25 plus 108, so that's 133, which means there'd be 2 solutions. Okay, and both are unique. Okay. Now, your textbook is going to go a little further than what we just talked about. The textbook is going to talk about real roots, imaginary roots, stuff like that. So, well, if we take a look at these first 2 examples here, these were the easy ones we started with. You get x plus 2 times x plus 2. And for this one here, we would have x plus 1 and x plus 4. So we get answers x equals negative 2, negative 2. And like I said, we wouldn't write them both down. We would just pick one. So we would say that there is one real distinct solution. For this one, we would have x equals to negative 1 or negative 4. Where this time we have 2 distinct solutions. But we may also describe our answers as imaginary. So let me show you here what happens in the quadratic formula. If we tried it with this, we would end up with 1 minus 4 times 1 times 10. So we would negative 39. That means in my answer for the quadratic formula, there'd be a root 39, negative 39 somewhere. So that would cause some problems, obviously. But as I mentioned, mathematicians have this way of dealing with things. Usually when things don't turn out the way they expect, they just make an exception. So the exception here is we could come up with a whole new number system, imaginary numbers, which are based around this idea of the square root of negative 1. And it's usually given the letter lowercase I. So if you look in your textbook and at the back it had an I somewhere in the answer when you're checking over your answers, then they're talking about square root negative 1 when you see I. The 2 are used meaning the same thing. Now why on earth would you want to study imaginary numbers or something that even sounds, I mean, how much do you use this math and then you've got imaginary math? Like, come on, right? But if we had an example like what we've already been working with, this is going to be 9 minus 3 root negative 1, I'm sorry, plus, then this will be minus 3 root negative 1. Multiply those 2 together, and I get minus square root negative 1 all squared. So I'd have 9, those disappear, and when I square this, I actually come back to the real numbers. So there are instances that it's definitely worthwhile to study imaginary numbers because we get back to the real world when we do our intermediate calculations. So those of you who are going on to do electrical engineering, you're going to be so familiar with this. It's going to torture you in your sleep, I promise. Okay. So use the language, how many, unique, real, imaginary, to tell me about these equations and their solutions. Okay, so for this one, 4 minus 4 times 3 times negative 9. Looks like I have 112. So that means I'm going to have 2 distinct roots. And they're both real. Okay, for this one here, it's going to be 16 minus 4 times 1 times 4. So there's going to be 1 real and unique root. 25 minus 4 times 2 times 7 means I'm going to have negative 31. So this is going to have 2 imaginary solutions. Over here, 21 squared will be 441 minus 4 times 4 times 9 is 297. So the number is still positive. It means I'm going to have 2 real and distinct roots. 25 minus 4 times 2 times negative 1, that's 33. So again, I would have 2 real and their distinct roots. And then on the last question, it would be 4 minus 4 times 1 times 3. So this would be negative 8, which means I'd have 2 imaginary solutions. So, again, be careful when you're dealing with equations like this. They need to be sorted out. So we're dealing with x squared minus 6x plus 5, x squared plus 2x minus 1, before you end up going and moving into your discriminant.
Plus.
Sorry?
It's plus 1 or minus 1?
Plus 1, yeah, thank you. Okay, so now just to see how we're doing with the discriminant, we want to work backwards.
For the 2 imaginary thing, is this supposed to be a 0 solution?
Yeah, there's no real solution. This is just some of the language you'll encounter. So for me, I'm happy if you say there's no solution. But if you were to read multiple choice or come across the answers in the back of your textbook, it may not say no solution. It might instead say 2 imaginary answers.
So 2 imaginary answers are the same as the 0 solution?
As the no real solution, yes. For the parabola, that's what will happen. Okay? So this time we're going to think backwards, which means we have to figure out how is it that we're going to get